Hi, everyone, and welcome to this 11th week of BIOB20. So this week's we're going to see different topics, in particular regression, coefficients of regression, etc., coefficient of correlation, I meant. But before we do this, are there any questions or things you'd like me to explain or to go over again? And I've heard that maybe going to the logical flow of tutorial 10 about confidence intervals would be useful.
Yeah, so I think in particular, the first set of questions, we compare all the different like the so we do chi-square, we do Fisher test, and then we also use like we also use P binomials with the value from
Yeah.
the binomial distribution.
Yeah.
And then in the fourth question, it tells us choose like the one that was also put there.
Yeah.
And I was like, I kind of like guessed it. I kind of like was like, okay, well, I don't really understand if I'm choosing this one. This one sounds almost certain, but I don't really understand why.
Okay, so the question is like we had three possible tests. Question 4 was like choose the best, and so why is this the right answer? So it's a bit of a matter of details, but every time you have a test, you make some assumptions about the distribution of a certain statistic, and these assumptions are either met or they're not met in the experimental protocol. In this particular case, it was difficult, and that's why I made an announcement that it's not clear whether they were met or not. And I've insisted a little bit at some point that if the test is well made, then you should be able to have the null distribution before you get the data. If you need the data to get the null distribution, then you want to believe. You're in this I want to believe mode because you're making your assumptions and your expectations based on what you've seen already. So you broke, I mean, this is circular reasoning, so you cannot do that. The whole idea of statistical tests is to make expectations that are separate from the results, that you stop the cycle of belief. Sometimes it's difficult, though. In particular, there is this one case which is kind of a problem in my discourse, is that in the case of clinical trials, there's a tolerance for not specifying literally everything. And in particular, in the case of this clinical trial here, mRNA-1273, they came up with 196 participants who were sick, and this comes a little bit out of nowhere. And what seems to be the case is that they have just stopped the clinical trial whenever they felt like it. Like this is long enough. We have waited long enough. Let's see how many people got sick. Well, sir, it's 196. Okay, let's do that. But then they could not have predicted that it was 196 before they get the data. So in that case, they have broken the magic rule that they could get the expectations without even having the data just yet. Yes.
But they can also calculate the power for their test to determine the number of people required.
Yes, they can compute the power.
So then you could still technically determine the number, a number of people.
Yeah.
And you'll be have to stop it. That's part of it.
Yeah. So this particular topic of discussion is hotly debated, whether it's okay to stop a clinical trial in the middle or not. And you have two sides, and they're very argumentative about their opinion. Some say no, like you have to respect the protocol, otherwise you're not doing it the proper way. And some have the exact opposite opinion, say no, like this is fine to stop it whenever you want. So there's not even a huge amount of agreement about this, but definitely there's a tolerance to say, well, it's kind of fine. They stop wherever they stop, and then they count, and they get 196, and we're going to pretend that they always wanted to stop the trial at 196. It's fine. And in practice, it's probably fine. Of course, you see that this can be a problem, like ethically and methodologically. If there's someone keeping an eye on the counter and then also on the results, and say, we stop it now because the results are good, and if we wait a bit, then like numbers can change, etc. Then this is bad as well. So if you allow people to stop the clinical trial, you're also allowing some abuse to take place. That's a little bit one of the possible issues with it. But if we exclude that and we say, well, it's also complicated to run clinical trials, etc. We have to give them a little bit of the benefit of the doubt. We can pretend that 196 was fixed from the beginning, and that's what we do from question 5 forward, etc. We pretend that this is something that they had set. But out of these three tests, of the questions 1, 2, and 3, like the chi-square test, the Fisher test, and the binomial test, only the chi-square test kind of does not require this 196. And that's the point, is that if you use the Fisher test, remember that you have to fix the margins of the 2x2 table. So you can perform the test in practice, but that is valid only if the way in which you resample the data was kind of working with fixed margins. And that would be possible only if they had decided what the margins should be beforehand, but they hadn't. In this case, it doesn't look like they had. So the Fisher test, well, you can perform it, but that doesn't really correspond to what has happened in the trial. The binomial test, you can also perform it, but you need this magic number 196, which you did not have before you started to record the data. Only in the case of the chi-square, you do not need that number, and you're fine. So that's kind of the philosophy, if you want, of the question, to say one of the tests is a little bit better, resistant to the fact that these guys haven't really done exactly what they say they've done, because they did not need it. Like according to the chi-square test, you can pretty much stop it whenever you want, as long as this is random stopping time and not something that's based on looking at the result and stopping when they're optimal, then it's a little bit more appropriate. But that's still not the test we're using, because everything's complicated to compare, to compute confidence intervals with the chi-square is particularly difficult. And that's the point of question 16, is to say that you can do it, but in the end, that gives you something that's highly non-intuitive. So it's better to cheat a little bit, use this tolerance that we have, and get intuitive results using the binomial distribution, even though the null distribution is not exactly the same, but the interpretation is easier. That was the idea. Did you have another question about the logical flow of tutorial 10?
I remember like I asked you this thing, but I couldn't respond to me, and I still didn't really quite get it. It was the question 5 where you define the probability successfully 1 minus divided by, like not 1 minus. So why is that the problem? Why is it not just 1 minus?
Yeah. So question 5: why is the probability of success this weird thing here and not 1 minus theta? It's just because of the way the efficiency is defined. If the efficiency is 0, you have as many vaccinated people as placebo people. So then it's 50-50. So an efficiency of 0 corresponds to 50-50. And the efficiency of 1 means that they're all placebo in the group of people who get sick. So if you do 1 minus the efficiency, well, it would be 1 or 0, not 1 and 0.5. But with this formula here, when you say the efficiency is 0, that makes 1 minus 0, 1 divided by 2, that's 1/2. So that gives you the correct result. It's just because of that. It's a correction that you need to apply for the fact that people are coming also from the placebo group and not just from the vaccine group. It's this. I should have mentioned this because many people got a little bit like, what the, with this formula, and it's just this. Right, for the sake of time, I think I can take one extra question if it's really important about tutorial 10, but otherwise we need to make progress with 11. Okay, so let's move on. We're going to close that for now. And we're going to now talk a little bit about pairs of variable. And the way we're going to start this class is really with an example in which we kind of know the model, and we're going to know everything that there is to know, because we're going to plug in the numbers, and we're going to try and play rediscovering them from the data. So we have two variables, x and y, and we're going to say that x here, as usual, is a bunch of random numbers. And so they're just Gaussian, centered on 0, nothing strange or even original here. And the new thing this week is that we're going to say that x is a function of y of that form, a plus bx. So these a, b lines, like this is really a straight line. When you plot y against x, you get a straight line, and a is called the intercept, so that just shows how high the line is, and b is the slope, that shows like really whether the slope is one way or another. And we're going to say that because that'd be very boring if we knew everything, we're going to add a little bit of noise here. So our norm, so we're going to have something of that form that has also a random noise added to the line. So the values of x, they could be anything. They don't even have to be random. They could be deterministic. It's like x does not even have to be a random variable. The only random variable is going to be actually this bit here. And just to make sure that this point hits home, I'm going to say that x is not even a random variable. It's going to be a sequence from minus 100 to minus 100 to plus 100. Okay, and by 1. So like x is length 201. Oops. And length, I don't know. 201. And y will have this form here. Okay, so except that now we need 201 number to make the noise, and we're just going to choose two numbers, arbitrary numbers for a and b, and we're going to try and play to rediscover them. We're going to say that a is going to be 1.2, for instance. No, we're going to say that this is 0, okay, like for that particular example. So like y is just a like linear number times x, and b, we're going to say that this is, I don't know, like 2.3. Whatever. Okay, so x is a deterministic number, y is a deterministic function of a deterministic number, so that's the deterministic part, but the only piece that's random now is this random noise that has been added on top of y. So let's see what this looks like when we just plot one versus the other. Okay, so I'll probably have to change my numbers a little bit, because now this is a little bit too deterministic. Okay, so I'm just going to change it to make it more, a little bit more random. So instead of x being everything from minus 100 to plus 100, I think from minus 3 to plus 3, and to say that the length is going to be 201 is going to give us a better, going to be more fun this way. Okay, so basically we have x, which takes all the values from minus 3 to 3 in a sequential order. But as you can see, the values of y, then there is this noise that has been added here. And that makes it so that y still feels like this is a linear function of x, but not completely. There's a deterministic part. So many problems can be cast in that framework here, where you have a variable that depends on another that keeps increasing, but you have a bit of fluctuations, random noise that are due to the processes happening around whatever you're measuring. And that means that this relationship is not pretty deterministic. So the example that comes to mind is height versus weight, for instance. Like you have all these things where one increases, the other increases as well, but with a bit of noise. And you have so many cases that fall into this category. And the game now is to say, based on that, when we have just these points here and we don't know the value of b, which is 2.3, how can we get the value of b here? And many of you, I suppose, have seen a method which is called least square estimation. So they say, well, why don't we find the lines there that will minimize the square of the distances between the line and the points? And you say, sure, why? Like, why exactly? You have other criteria. You can also take the minimum difference in absolute values instead of taking the square. What is taking the square? What is so magical about it? Usually people say, yeah, just shut up and do it. So the reason is that it's got nothing to do with the square. It's just that this is the maximum likelihood estimation of that model. We have assumed that the deviations that we've got on this line here are Gaussian, and the way that we're going to solve that problem is going to be equivalent to minimizing the least square. It's exactly the same solution in both cases. We're going to demonstrate it now. And so, of course, it's much easier to say we're minimizing a score that you guys have learned in high school, rather than saying we're minimizing a score which is much more advanced, which is the universal information score, which is the likelihood. To say if you know something about something, then that translates into a likelihood. So it's much more coherent to say that when we're maximizing the likelihood, which is finding the value of mu, which is b, which is the most likely based on our assumptions, but this is more advanced, and this is why people don't say that. So here we go. We're going to solve this problem using the maximum likelihood estimation problem. And because the only thing that's random here is this bit here, this is this Gaussian variable, everything else is deterministic. Like the only thing that can be random is this Gaussian random bit, which is the vertical deviations here between the line and the observed points. I'm going to put the line actually 0 and 2.3 here. So this is the line. This is the relationship between x and y, and vertically, the vertical distance, like y deviates vertically through a Gaussian random variable. And so the way we're going to solve this problem is going to try different values of b here and find the one that corresponds to just the maximum likelihood. So because we have a Gaussian random variable, the maximum likelihood will always be of the form d norm something. Okay, that's always the way that we get a probability for a Gaussian distribution. So what is going to be this d norm here? Well, we're going to say that this is, of course, the difference between the vertical data point and the slope here. Okay, but because we don't know the slope, we have to propose something, and we can compute the d norm only on something that we propose. So I'm creating this variable y underscore to say, or y predict, okay, to say that this is the value of y based on a particular prediction. That would be that if I believe that, for example, b is 1.1, it'd be 1.1x. Okay, so that would be my attempt here at predicting the where the slope is with 1.1, for instance. I'm going to draw here this curve in blue. Okay, so I'm just trying this thing here, and I'm going to try them all. So like, there's nothing special about this particular blue line. I'm just starting with this one, but I'll go systematic at some point. But still, for concreteness, it's good to show what happens with one example. So now I'm computing the distances between every of these points here and the blue line. That's really what I compute the d norm on. All right, so if all I know about the model is that it's of this form here, it's a or b times x, but I don't know b, and then plus a Gaussian noise here. The way I compute the likelihood of one particular parameter b is to say, well, I'm taking the vertical distances, so y predict minus y. Okay, these are all the vertical differences between the data points and the blue curves. And there are 201 of them. And I'm plugging this into a d norm. And that's really the likelihood of the observations. Because I remind you that this here is the only random part. So I got 201 numbers. What they are does not matter very much. I'm taking their product to get the likelihood of the whole thing. And of course, the problem is that you see that these numbers here become very, very, very small now. With the size of 200, we can still encode them on the computer, but this is really high time I switched to using the logs, because these numbers, they're way too small that they can be trusted. The mathematical operations on the computer are no longer guaranteed for anything that's lower than 2.2 10 to the minus 16. So this is way too low a number, and I have to switch to the logs now. So I'm doing this by saying d norm log equals true, and I replace the product by a sum. And what I'm computing is no longer the likelihood, but the log likelihood, and the log likelihood is minus 672. That's a number which is much more easy to store and to display on my computer, and for which the mathematical operations are guaranteed. So this one, it's fine. It's not going to underflow or to give me some mathematical errors just because the numbers are impossibly small to store on the computer. So these things we've seen multiple times. We've done it already. The only new thing is that now we're tweaking a parameter which is not the ones of the distribution directly. Usually we're tweaking mu, we're tweaking sigma, we're tweaking lambda, something like this. But nothing ever told us in this maximum likelihood approach that we could only tweak the parameters of the distribution. Here, I can tweak any parameter and then compute what is the probability of observing what I observe if I believe that B is equal to 0.1. And the probability, let's say it has a log likelihood, which is extremely small here. So that's not an extremely good guess, as we can see anyway. It's kind of too far for being a plausible explanation for the data that we observe here. So as usual, what I do is that I'm going to try all the values with a certain coarseness, and one of the values is going to give me the best possible likelihood, and that's going to be the one I choose for my estimate of B. And the best way to do this is, of course, using a for loop. So I'm going to say the values of B that I'm going to try is going to be everything from, I don't know, it seems that this is positive. I don't need to try negative values, so anything from 0 to, let's say, 3. So from 0 to 3 by 0.1. Okay, it could be anything smaller than this, but like that gives me just a couple of values to try. I got 31 here, and now I need to compute the log likelihood of each of them, and I'm going to use exactly the same method here, well, actually that one, to get the log likelihood, and I'm going to pick the max of the curve as usual, and that's going to be my estimate. So I'm taking the log likelihood, and I'm saying that I want to replicate 30 times the value NA because it's a nice value for initialization, and I'm now going to fill the LL vector. So for I in 1 to 31 values, and I'm saying at the position I here, this is going to be the log likelihood here, except that I need to compute again this new predicted value based on the new value of B. So I would say that something has to come before, and that's here. My prediction is going to be B times X. Okay, except that this is the B, the ith value of B times X. So I'm trying all these things. Typo. Where did I make a typo? Predicate. Here. Right. Is there another one? No, it's good. So we're trying all the values from 0 till 3, and I'm just computing my score, which is the always the same. It's always the log likelihood. So let's see what happened to the score. Yeah, it's been filled. There's no NA anymore, so everything has been filled. Now if I plot B on the x-axis versus LL on the y-axis, and I'm going to say I want a nice line, I got something like that. Okay, so for 0, the log likelihood is below minus 1,500, so very, very low, and it keeps rising to something at around 2.23, something like this, and then it goes down again. So this is it. If I say that B is equal to the maximum that it is here, which is going to be 2.3 probably, then all the observations are the most plausible. Okay, that's the one for which, because we know that there's a Gaussian noise, that there's a Gaussian difference, etc. And for that particular value of B, then the part that is random is the most plausible. The part that's deterministic is deterministic, but the part that's random doesn't ask me to make crazy, impossible assumptions about things that are miracles. These are things that are just happening. They're as plausible as possible. I have few miracles here, and I have many miracles here, so I take the explanation that has as few miracles as possible. So, which is the max of LL? Give me the index. It's 23. Okay, and B at position 23 is 2.2, so I missed. The true value was 2.3, I think, but I got 2.2. And as you can see here, it's a close call. The first 2 or 3 values are almost the same likelihood. And so that's good enough. That's my estimate. I would say that the at least with that level of coarseness, my estimate of B is going to be 2.2. So far, so good. That's something that we saw in the video, so it's just good to have a bit of a rehash of it. Now let's see what happens with the other method that some of you have known, which is the least square method. So how would that work? We say that it's again we can put that into a for loop, and instead of taking LL for the likelihood, we will say the SQ for squares. And so we'd say that because we're taking 30 1 values. I'm again initializing SQ4 squares. And now in my for loop here, I would do kind of the same. I try all the values of the slope, just the same between 0 and 3. And instead of computing the log likelihood, I would compute the squares here, which is actually the sum of the squares. So how does that work? This is the sum of y predict minus y square. That here is the least square criterion. That's what I would do. I'm just computing the vertical distances, squaring them. I can compute the mean. Maybe that's going to be better instead of the sum, just so that the numbers are a little bit lower. But that's kind of what I'm doing. And I'm trying all the possible slopes every time, computing the vertical distances between my prediction here and the actual values, squaring them, taking the mean. I mean, I think it's the sum in the original definition. Doesn't matter very much. And this I'm storing in square I. And now if I'm plotting a new plot here, in which I'm showing, instead of P and LL, I'm showing B and SQ, right? You can see that this is the opposite. Actually, these two curves here are mirror image of each other. That this one here has a minimum here at the place where this one has a maximum. The y-axis is of course very different because these are mean squares taken over 100 points, and this is 0 probability. But the point is that this is literally exactly the same computations. The log likelihood is only a function of the sum of the squares, and this is why picking the minimum of that curve here is always going to be exactly the same as picking the maximum of that one. You cannot get one without the other. It's just two sides of the same coin, except that one defines it through probability, this other one through the least squares. So if you know the least square method, then welcome. Like you've just realized that all you were doing all this time was actually maximum likelihood estimation instead of minimum least square. And if you did not know the least square method, then it's fine, you don't need it. Like this is one way you can compute it, but it's more logical to think about it as a maximum likelihood estimation. So they're one and the same. Okay, so that's the part about the way that these things are done internally. So it's not just that the least taking the square of the distance is something that is pretty better than taking the absolute distances, etc. Is that boils down to the fact that we have assumed that the distances were Gaussian. Right? If you believe that the noise that you have in your slope, the vertical noise, is Gaussian, then you have to use the least square method. It's the same. But if you don't believe that this dispersion is Gaussian, then you have no reason to also use the least square method. Then it's not going to be a better curve than anything else. It's the best curve only if you assume that the dispersion is Gaussian. So in practice, many problems are more complicated than the one that we've seen here. Like we've said that y is 2.3 times x, and that we have a Gaussian noise here. But most problems will be a bit more complicated, that you also have an a term here. Okay, so first of all, we have completely neglected the fact that the line can actually vary in position vertically, and that's the intercept. And the second thing is that here we have made a noise which has standard deviation 1, like mean 0 and standard deviation 1. So here we can also have SD equals, I don't know, something else. And you don't get exactly the same log likelihood if you say that the standard deviation is 4.5 or if it's 1. So you would have to estimate A here, B the same as we did it, and the estimation also depends on the value of the standard deviation here. And that's not something that we cannot do. That'd be even relatively easy for us to do at that stage. We're good enough, but it's still a bit tedious to estimate 3 parameters at the same time. And so we're just going to skip it. I think by now you know that it's just a matter of finding the maximum of the function. You have 3 parameters to tweak. Fundamentally, This is a little bit more tedious, but there's nothing fundamentally different in terms of methods. So the way that these problems are solved is not by computing manually the log likelihood, but by asking R to do that for us. And the way that this is done is that we use, for example, this is called a model, a linear model, and we use the function ln, that stands for linear model, here, and we plug directly x and y. Instead of saying x comma y, which is like most functions in R, this one has got a very particular syntax, and that's something that's kind of, I'm still wondering a little bit about this. Why this particular syntax? Like this writing here, y tilde x is used only for the function ln in R. Like there's not really any other function that uses this particular notation. Of course, the function ln is very frequent, but let's say it's still like the fact that it would have its own syntax is kind of a little bit weird. So the model here is fitted with this function lm, and then you use y tilde x. So it means that y is a function of x. That's what it means. And not just that, it means that y is a linear function of x of the form that is here, a plus bx, and that the residuals here, this is called, are Gaussian. So when you do this, this runs relatively fast, and that has done the fitting for you. It has used the maximum likelihood estimation method, which comes down to the minimum, like the least square method, and it has found the value of a for you, the value of b here. It has also estimated the standard deviation of this extra noise here, but it's usually not showing it for you. Okay, so I'm going to create here an example, a new example. Here we go. With these values, I need to find a value for a. We're going to say 1.2. So now when I do the model here and I say model, it gives the information that I was after. So it says that the formula is this: y is a linear function of x of the form a plus bx plus a random Gaussian noise, and I get the coefficients, which is most of the time the information that I want, like 1.194 for the intercept. So you can see that this is quite close to the actual one. So the actual was 1.2 and it says 1.19, not bad. And 2.3 for the slope. Well, it's a bit less good here. Okay, like it was accurate to within 1% for the intercept, and yet this is clearly not accurate to within 1% for the intercept. It's not super far either, 2.3 versus 2, but you could see that estimating the slope is always a little bit more difficult than estimating the intercept here. So those are my estimates here, and that's something that's quite useful to have. When I type just model here, get that, but model has got many more interesting things inside. When I type model, it just displays some of the features that are in the model. If I want to see the internal structure of something in R, I use str. Yes. That's a very good question. So if the standard deviation of the noise was much lower here, let's say something like really, really small like that, would we get a better estimation of A and B here? What do you guys think? Yeah, so if it's 0, then it means it's going to be deterministic actually. So the estimation is going to be unproblematic. So here when I do the estimation of the model, you'll see that it's pretty good already because there is no randomness anymore. So what creates the difficulty of the problem is that when the dispersion increases, then you have multiple lines, that gives wiggle room for the optimal line to be. And like you will find the way to place vertically the line. It's going to be okay, but you always have a bit of doubt for where to place the like the slope. And the more you have a span on the x, the more accurate the slope is. Right? So if your x values are really squished together so that you don't really span it off, then there will be multiple lines that will be able to fit. So in general, if you want to get a good accurate measure of the slope, because x does not even have to be a random variable, you can just have it as a controlled variable. You will push on the extremes to try and get as many values on the extreme as possible to calibrate your curve quite well. So the answer is yes. The more noise you've got here and the less accurate the parameters are. I'm going to bring back some noise, that's 4.5, to make it a little bit more noisy and therefore entertaining. And so now, yeah, no, not so bad this time, but it's A this time that was not entirely well predicted. So the model here gives you the formula, the coefficients, but there are more things. And I was about to say that when you have complex objects in R, there's this function called str that stands for structure that gives you a lot of information about complex objects like a model. The model is kind of a list of lists. So it's a kind of a recurrent object with plenty of interesting things. And you can see that it has something that's called coefficients, residuals, effects, rank, fitted values, assign, QR, etc. So there's a lot of things that you can look into, especially this is described all in the help page of the function lm. And the ones that I'd like to draw your attention on are coefficients, for instance. That's the one that we just looked at. So that's the intercept here, and the one that's called the name of the variable in x in that case. So coefficients, we just saw them. Residuals, what is it? So the residuals are the vertical differences between the line and the actual data. So if you plot them on a very simple plot, what you get here is you see a straight line at 0, and this is really the Gaussian variable that you have added on top of the linear strand. So you have something that's increasing like this, and you have added kind of a random noise that was within 2 bounds, and that's what you're plotting here to see these values. There is an interesting outlier here that is way, way too high compared to the rest, and yet that is perfectly random. So that thing has happened perfectly normally in the course of the simulation, an outlier like this. And that's a way for you to check that, is this Gaussian? Like, does that really correspond to my assumptions, etc.? And in principle, that should be the case. The residuals is, by definition, the random part of the model, like this noise that you have added to the deterministic part. And so when you have the residuals, what you can do is to compute the SD, the standard deviation of the residuals. And that here is your, is your estimation of the missing parameter. Okay, so once you have the residuals, this is really these kind of Gaussian centered variables. Just taking the standard deviation should give you an estimate, and that's actually the maximum likelihood estimate of the standard deviation that you have used in the Gaussian sample in the beginning. Okay, so the LM object, what is output by the function LM, contains a lot of information in addition to the coefficient. It also has the fitted values. The fitted values is, if residuals is the difference to the line, the fitted values is really the points on the line. So if you do plot model fitted values, then what you get is the deterministic part. Okay, and if you do model fitted values plus model residuals, then you get the initial data that you had. All right, so it kind of decomposes your data into the deterministic part, which is the fitted value, that's the A plus BX, and the random part, which is the residual. All right, does that make sense for you? Are there any questions about this, about the use of the LM function, etc.? All right, so the LM function is, you understand it, a bit of a automatized maximum likelihood estimation on 3 parameters. 2 you deeply care about, that's the intercept and the slope, because they will tell you how the deterministic part is. 1 you less deeply care about, which is the amount of noise that is in the model. It is important for some applications, but most of the time all you want is the line, right? So one thing is that we have a random part in the model. What is the random part that we have so far? It's not X. Y is random, but not even every part of Y is random. The only thing that's random is the so-called residual, like X is deterministic, A plus BX is deterministic as well, and then we have this random part, which is the added noise. What about the model coefficients? Are they random or are they deterministic? What do you guys think? Like not the true A and true B. Like when I say, for example, model coefficients, like these things here, is this a random variable or is this not a random variable? It's a random variable, okay? It's a function of a random variable, therefore it's a random variable. Anything that takes random numbers as input is random. So these things, they are estimates. So we know that if the sample size increases to infinity, then they will kind of converge very nicely to the correct value. But before we get there, then they are kind of probably calibrated around the proper value, but there is some uncertainty about it. There's some dispersion. And one of the questions that we can have is, okay, that's an estimate. This is not the true value. That's an estimate. This is not the true value. What do we know about the true value? Like, is it possible, for instance, that the true value of the coefficient is 0? And we can ask these kind of questions because now what we have is only a random number that represents that value, and that random number has a certain target position, but also a dispersion around it. So question is, based on what we know, is it possible that the value of B was actually 0, and because of the game of dispersions, then I have estimated to be a little bit too high. So these are the kind of things that I can do with a statistical test, of course. I can make a null hypothesis that says, I assume that B was actually 0, that the line was actually like this. I don't know what is A, so I will allow the line to shift vertically like this. But I'm saying that my null hypothesis is that B is 0, and A would be a nuisance parameter, and that there is a Gaussian dispersion around 0, and that the fact that I find a slope that's like this is just an illusion that sometimes when you draw the points, well, yeah, they will be a little bit crooked, a little bit shifted, and then they will make a slope that's like that. Is it possible? Yes, no. We set up a statistical test, and the way to do this, the easiest, is to use the function ANOVA. You just ANOVA on model, and it performs what is an ANOVA test. It's a fascinating topic that we won't have time to cover at all in this course. Like 12 weeks is too short to cover ANOVA, even though this is one of the most interesting topics. I've decided to not cover it because I would not be able to cover it in sufficient length to make it interesting. But all you need to know is that this is a statistical test. That's the same as t-dot test, Wilcox test, chi-sq test, etc. You have many automatic tests in R, and now we understand the logic. Like there's a null hypothesis, there's the score, there's a null distribution, and then we can just look at the position of the score in that null distribution to reject or to accept. And the p-value is given here by that last column, probability that the distribution that you observe here is greater than, probability that the null distribution, that an f, which is according to the null distribution, is greater than the probability, than the value that you observe here. So that's the p-value, and that's the score here. Okay, and you don't know the threshold, doesn't tell you that. But the p-value is really small here, or does not give the p-values below 2.2 to the minus 16, and I explained to you the reason is that this is the minimum number for which arithmetic operations are guaranteed. For a number that's smaller than that, the computer does not even guarantee that it will be able to compute properly additions, multiplications, etc. So below that number, OR says, don't bother. We could give you a p-value if you want, but this is just like uninteresting to compute p-values below this. It's long past uninteresting, actually. So we reject the null hypothesis in this case. And the null hypothesis was that the coefficient of x, b, in that case, was 0. And so we reject that null hypothesis. That's a very simple way to run this test. And the test is actually quite complicated inside. It uses distributions that we have not even talked about, which is the Fisher-Snedeker distribution, the F distribution. But it doesn't matter what it is. I think by now you can imagine that some very smart people have discovered a very smart score for which they can have a very smart null distribution on which they did not need to know the data beforehand. It's always the same story. And so once they calibrated these distributions, they can run the test with it. Okay? So a model is kind of nice because it gives us the estimate, but these estimates being random variables, then we can perform statistical tests with it. And so in that particular case, we can reject the fact that b is equal to 0. It's not consistent with the data. So we can reject with high confidence even. Okay? All right, we can do more than this. We can do confidence intervals, of course. Once you can make a statistical test, well, you can make a confidence interval. The only thing you need to do to make a confidence interval is to be able to change the hypotheses. So this is the p-value that's associated with b equals 0. Well, you do the same. You say, what about the p-value associated with the null hypothesis that b is equal to 1, and then 2, and then every possible value. And when the p-value is relatively high, well, you keep these values in an interval. And so you can, if you can make a test, in general, you can make a confidence interval. So that also gives us access not only to the maximum likelihood estimation, but to the confidence interval estimation. And you will see in the tutorial 11 how to build these confidence intervals. By the way, I've tried to make tutorial 11 relatively straightforward and easy. I hope that I succeed. The reason is because I'm going to release the final exam, hopefully tonight. Okay, so I will give you something like approximately 2 weeks for the final exam. We need to have it wrapped up pretty much at the beginning of the final exam seasons for technical reasons. And so that's why I'm trying to make the tutorials a little bit low key so that you can focus on the final exam. I may release it in 2 rounds. So you're gonna have, I think, 5 problems of different difficulties, and it's going to be quite similar to the midterm, like nothing really fundamentally new. We're going to play with the same ideas of questions that we had. So you'll see this. It's possible that I release it in 2 rounds because some parts are ready, and I wouldn't like to wait too much so that you can already see the questions and prepare for them, etc. Some others are not yet ready, and I don't think that this is nice to wait too much. I think 2 weeks is going to be good so that you can start to work on the problems. So yeah, I would like you to work on the final exam, and this is why I hope the tutorial is going to be relatively smooth. Development bonus points, I don't know. This is hard to know. Anyway, so that's final exam stuff. Let's go back to where we were. This is explained in the tutorial, and like I said, the tutorial is calibrated to be relatively straightforward, like do this, do that, learn this, goodbye. I hope it's going to be this way. If it's not this way, if it's way too hard, please tell me, because it's not supposed to be too hard. The last 2 tutorials are supposed to be relatively easy. So we can also, as usual, like if we have an estimation method, then we can often, with that score, we can build a test. With that test, we can build a confidence interval. So everything kind of falls into place. Once we understand how the theory is built, we see that as long as we have a score that we can compute the distribution of, we can use the whole kind of tool set of classical inference, classical statistics there. And one thing is, of course, we did all this so that we can see which line that corresponds to on the graph here. So how do we add the regression line on the graph that is here? This is particularly easy in the case of linear regression because the function AB line nicely fits with the model. So if you just say AB line model, in principle, oh, well, that's fantastic. So let's plot again X and Y. Okay, and so if I just say AB line model, then that already gives me the line that is the regression line. This is a fairly simple interface when you want to add a particular line to a graph. But if that line is itself the linear regression model of the points, then you can do it this way. As long as the model is the linear regression, that works fine. So if you have, in the generic case, you have plot xy, you can just do directly AB line LM linear model of y regressed on x, and that gives you that line here. Pretty simple way to plot it. So far, so good. All right, we're going to take an example that will show that linear regression is awesome, but there's still, this is not the end of the story. Like there are some things that are kind of, a bit limiting factors with a regression line. And I'm going to introduce you, if you don't know it, to the iris data set. So there's this nice function in OR, which is called data, and that allows you to load in your session some epic data set. And there's the iris data set, which is something that was prepared by Ronald Fisher and has been used by multiple generations of statisticians. So pretty much by now, millions, if not hundreds of millions of people have been tortured with this data set. And I thought, well, this is now time to torture you guys. So Fisher was extremely interested in irises, and so being also extremely interested in statistics, as you know, and he has prepared this data set that they use for multiple teaching purposes. And this is a data set with 150 rows, and this is just the first 6. And he measured the sepal length, the sepal width, the petal length, the petal width on 3 different species. And it really doesn't matter exactly what they are and why he did this for. What matters is that we have this very simple way to conjuring up some data in our session so that we can do some mathematical applications with it. And here I'm going to do the very obvious, which is to plot the sepal length versus the sepal width, the first 2 columns. And I will use that to make a point, basically. So here we go. I'm saying x is the sepal length and y is the sepal width. So we got the points here. And because of what I'm going to do next, I will just decide to say that I'm giving each of them a different color. It's just to make them, and I'm going to change as well the this thing here. So it's just so that we can see a little bit better what is what. Otherwise, everything will look the same for what I'm going to do next. So that's the way it looks here. And I'm going to say, very interesting, I'm going to make a model in which I do the regression of y over x and see where this line is. So here we go. This is already something that's fairly easy for us. Now we say model 1, in which we take the linear model of the y-axis is this one here. This is sepal width. And I'm doing a regression on the x-axis, which is this one, is the sepal length. And I'm doing AB line model 1. Ta-da! This is extremely beautiful. Okay, this is a fantastic model here. Well, okay, interesting. But I've taken x as the sepal length and y as the sepal width because sepal length was the first column and sepal width was the second column. But there's no reason to actually choose that. What about I just flip the axes and I say, you know, like there's no reason why this is the intrinsically better choice for x to say that the sepal length is intrinsically better. So here we go. Let's plot the data in another way. So I'm going to create a new window for my new plot. And we're going to bring in, we're just going to swap the axes, basically. We're going to say, what about the 2 columns that be in another order? And I would plot them in the other order that it would have been given. Nothing essential is going to change. So I'm doing this exercise here where I'm putting now in x the sepal width, and this is where I put some colors, so that you can see what happens to the points a little bit. Okay, when I shift it, it's not extremely easy to see that this has been flipped like this. That this is a symmetry with the first bisector, but these 2 points that are here, they used to be there. The points that are here are now there. The point that were here are now there, etc. So it's the same points, but they've been a little bit flipped around by a symmetry along the first bisector. I hope that this is clear to you all. And now, of course, in this representation, I'm going to do the new model, in which instead of doing the regression in this direction, I'm saying that the variables x and y have changed, and I'm doing the regression in the other direction. It's as simple as that. Okay, oops, that was supposed to be model 2. So I'm going to regenerate my model 1, and that will be model 2. And I'm going to add model 2 here. Okay, so here, this is the line that you see here and the line that you see there, and you say, yeah, sure, this is fine. Like both of them are okay. This is a good answer. But when you think about it, this line that is here, okay, that goes from the point that is there, that goes to these 2 red points that is here, it's a line that goes from here till there. Okay, they're almost orthogonal to each other, actually, these 2 lines. Right, so it's difficult for me to just draw the line, to draw this line on that graph. You kind of have to make mental rotations here. But look at it again, like, you know, it goes from these 2 points that are here, so it'd be here, and then on the other side, it's close to these 2 points that are there. So it's really going almost orthogonal to that line here. So what we're doing now is that we're saying, if we switch the roles of x and y, these lines are changing not just a bit, you know, they're becoming orthogonal to each other. So why is that? Does anyone have an idea why, like, that changes so much? Where is the asymmetry between x and y that's inherent in the linear regression? Where is it hidden? Because, like, something is asymmetric here, very asymmetric. And where was this assumption that I made that it would be so asymmetric? So the hidden assumption is that we said we're measuring the distance vertically, you know, that the noise is vertical noise. We said that x can be deterministic and y has a deterministic part, but this random part is vertical. We say that the random part is only on y and not on x. And then when you flip them, then you change that. You say now the random part is on x and that, and on the new x. So that is the reason why this fundamentally puts an asymmetry between the variables, and this is an asymmetry that is really, really hard to predict the consequence of. Okay, like, just to say that they're symmetric is, yeah, fine, but to the extent that you really have no idea what could happen if you do a regression in one direction or the other direction. And in some cases, it's not like one of the variables is really deterministic and the other one is random. Like in the case of the iris, for instance, they're both random. Like the sepal length and the sepal width is not like one of them can be set experimentally and the other one is measured, not at all. So what do we do in this case when we want something that is a little bit more symmetric, that we're not interested in having one being the controllable variable and the other one being the response variable? Well, in that case, you work with another setup, which is very much related, which is the correlation. So you compute the correlation between the 2 variables. So the correlation is very much linked to the linear regression, but this is still another thing. It's not exactly the same idea here. And tutorial 11 explains to you how to compute the correlation from the regression and vice versa. So if you have one, you have the other. But the problem with the correlation is that with the regression is that it's asymmetric. And sometimes you just want to know, are my 2 variables related? Yes, no. And so the correlation here, when I compute it with the sepal length versus the sepal width, this is minus 0.11. And if I switch, I say compute the correlation in the other direction, iris sepal width versus iris sepal length. Well, we're going to get the same thing because the correlation is this time symmetric. So it's a number between -1 and 1 that measures how much the variables are close to each other. So if the correlation is 1, the two variables are identical. So if I say, for example, iris sepal width versus iris sepal width, I'm going to get a correlation of 1. And it cannot go higher than 1. 1 is the highest value for the correlation at all. If the variables are inverse of each other, opposites, like sepal width minus sepal width, the correlation goes to -1. I've got a perfectly negative correlation. So it's always trapped between -1 at the minimum and +1 at the maximum. And if it's 0, it means that the two variables are not very much related at all. They're kind of independent, or at least uncorrelated. If it's very positive, close to 1, then the two variables are quite close to each other. And if it's very negative, close to -1, they're quite close to each other, but with a negative relationship between them. When one increases, the other one decreases, and vice versa. So the correlation is kind of an attempt at symmetrizing the linear regression to say when there is not one variable being kind of the consequence of the other, it maybe makes more sense to think about it as a symmetric relationship, where we give one number to say how much they are kind of bound together, and that shows when I know the value of one, how much that tells me the value of the other on a straight line. Okay, any question about correlation? So the correlation value here, it's pretty cool. You compute it this way. You can also do a correlation test. And again, it's the same thing, is that if you have, so is the correlation random? Yes, it is, okay, because it's a function of random variables. If it's random, then we can make an estimator. What the estimator is that particular value, the correlation, the Pearson correlation. If this is an estimator, we can probably use it as a score for statistical tests. So we can make that test here. And so if we do core test, well, I got the test here. And so it tells me that the p-value of the test is 2.2 to the -16, or less than that. And so what is the null hypothesis? Is that the correlation, the true correlation, is 0, as usual. So we reject the null hypothesis. And so here, of course, it's because I've used twice iris sepal. So it's not a very interesting correlation to compute. Let's compute it on sepal length and sepal width. Now the p-value is much closer to 1, okay, 0.15, that's a reject most of the time. Nobody has a threshold that is so high. Okay, so the p-value here is relatively high, we reject, so it is plausible that these values are actually not correlated, but that we still observe a value of the correlation which was minus 0.11 out of pure chance. Okay, and what's nice is that by default, when you do core test, you also get for free the 95% confidence interval. And now you're used to it. Okay, if we have a test, we also have a confidence interval that goes with it. That's pretty much always the case here. So my estimate of the correlation is minus 0.11. It says that this is anywhere between minus 0.27 and 0.04. That is at 95% confidence level. And because 0 is in the interval, then I know that I accept the null hypothesis that the correlation is 0. And I remind you that when I say I accept the null hypothesis, it is not exclusive. It doesn't mean that I accept this null hypothesis to the exclusion of every other possible value. I say that this makes this value acceptable. 0 is acceptable, but there's many other values that I accept together. Pretty much all of them which are in the interval, actually. I accept all these values. But I have accepted the one that is 0, so I don't have enough evidence to reject the fact that the correlation is 0. I don't have enough evidence to say that the two variables depend on each other. Okay, so far so good? Yes?
Sorry, just to ask about that last one. So, like in the instance, we've accepted the null, but we haven't, that doesn't mean like there are other nulls within the confidence interval. Is that why like the language in like some papers are like we fail to reject the null?
Yes.
Because it's more accurate than saying we accept the null?
Yes, exactly. We fail to reject the null is sometimes what you will see in the papers in the scientific discussion, scientific literature, because when you say accept the null, most people would implicitly assume I accept the null to the exclusion of everything else, which is like, I agree, this is a little bit badly said, accept the null. Like the statisticians speak about this without particular difficulty. For them, it's clear. But yeah, in the language, in the English language, when you say accept this, it kind of means that therefore I exclude everything else. Especially if your null hypothesis was so specific to say h equals 0, etc. It looks like you're accepting it to the exclusion of everything else. So I advise that you express yourself by saying, yeah, we fail to reject the null when you accept it, but that you still understand that when I say I accept the null, this is, but not exclusively. I would accept other null hypotheses, other hypotheses. So I'll still keep talking this way in reference to the way people express themselves in statistics, even though I have to admit that this is not the most clear way, that this is also confusing compared to the way other people speak. All right, so we've seen that when we have two variables that are quantitative, when we have two variables that are qualitative, by the way that we measure their correlations is with the chi-square test. Typically, we make a contingency table, we count, and then we test independence using the chi-square test. When the two variables are quantitative, we would typically use something like the correlation test or the regression to see whether they depend on each other, whether they are independent. And these two methods, like doing a regression or a correlation test, in the end, they will always give you the same result. When you test the nullity of a slope with regression, it's exactly the same p-value in principle as the correlation test here, because the correlation coefficient depends on the regression and vice versa. So internally, this is the same statistic, this is the same test, which is run internally. On the outside, if you want, the phenotypes look different, but this is exactly the same core. At the end, you have only one underlying distribution, but it's represented in different scores. So no risk in case you wonder that you would accept the null distribution, the null hypothesis with the correlation test, but then reject it when you do the same test with ANOVA on the linear model. Like usually, I don't think that you can have conflicts there because it's the same test that runs. So one thing that I like to show you now with the little time that we have left is a little bit how to make some kind of use of this for ggplot2 a little bit, because we've been plotting these lines with the standard OR library for plotting, but we're going to see a little bit how to use this thing with ggplot2. And while I'm at it, I'm going to show you other things with ggplot2, which are kind of nice to represent the data, because as usual, ggplot2 produces better quality figures than the ones of the standard OR library. So we're going to finish this session by a couple of ggplot2 lines, because everybody likes ggplot2. We're going to learn a few things about how to use colors, color gradients, and plotting lines with ggplot2. So we have already loaded the iris data set in our session. So we're going to use it to plot the data. And remember, for ggplot2, you always need a data frame if you want something to plot. And this is already a data frame. So this iris data here is kind of nice because we can use it as is if we want to plot a particular graph. So remember, the way it works is that we have ggplot here, and we have to start by specifying the data. So it's going to be from iris. And then we specify the aesthetics. And we want to say, for example, that x is going to be the first column, so sepal length. Oops. So cold that I don't manage to click anymore. And y is going to be the sepal width. So that is the essence, and then we have to specify the way we're going to represent the data. And remember that there's this geom something, and so for a scatter plot, we're just going to say geom point or points here, point. And we get this like this plot, which is already made with a little bit more style than the standard OR figures here with the name of the variables in X and Y, a grid, etc. And so before we show a little bit how to plot the lines, we're going to see how to plot colors, because that can be very useful. And the standard way that you do this, we have seen multiple ways, but one of them, which is kind of super simple here, is to say that we add to the aesthetics a color argument, and then we're going to specify one more column on which we're going to take the column from. So we could say color equals species, and there are 3 species in this data set. And remember that if you have a variable which is qualitative, it has to be a factor and not a string. But everything has been done nicely in this data set so that we can use it simply. So just say color equals species, and that does a lot of things which are quite nice for us. First, it chooses 3 colors that are different. That's amazing. And second, it puts automatically there a legend that says this color is that species, this color is that species, and that color is that species here. That does it automatically for us. Just by putting color equals one of the columns of the data set, it does all the hard work for us. Nice. But what about I put not a discrete variable here, but a continuous one? For example, I could say that I want a coloring which is based on petal length here. So here we go. Let's see what happens if that works. So what could that mean if we say that instead of putting something which is a discrete variable, we put a continuous variable? What is it going to come up with if it works? So the good news is that it does work. And the even better news is that it does something which is pretty nice. So it makes a color gradient here. I'm going to show you again the commands they're here. So it makes a color gradient automatically. So by default, when you don't specify anything, it makes this black to blue color gradient. The minimum value here is the one that's in the data. The maximum value is also picked from the data. And then it kind of scales everything. And the points, as you can see, are colored based on the value of the petal length here. Okay, so it looks pretty nice. I advise against it. Like everything that looks too nice is, of course, always very suspicious. So why do I advise against it? There's a lot of information here in this graph, and you start to have 3 variables represented. So the X and the Y are easy to pick because visually we have good representation of the space, but the color, like to know that this is 6 and that this is, for example, 3, is kind of hard because you have to refer to, sorry, 6. You see, I made mistakes. I'm making my point here. So these color maps, they're very beautiful, but they're not. There's no reason that they would be intuitive. So you always have to refer to the scheme to know which one particular value corresponds to. So what you know is that there is a gradient that's nicely represented with these points, but you don't know really which value the colors correspond to. Or to know that, for example, that particular color here is approximately twice as long as that particular color is really not obvious. Like you have to really look at the legend here and calibrate your colors based on what you see. So do it when you really want to impress your audience with very nice figures, very nice, beautiful colors. But otherwise, if you want to transmit information, the simplest is really to use the X and the Y axes the way they are. That's much more efficient. But at least that's super easy. Like ggplot2 makes it very easy for us to do that. So what about you don't like this particular color? You want to use something that is something different. So what are your options? One of them is that you can use, you can keep adding things to the ggplot line. As you remember, like, you have this ggplot and plus geom point, and then you can actually add other functions here, something like that. Scale color gradient is one possible way to add something. You say low is blue, high is red. So you're kind of changing the color gradient here to suit your needs or your aesthetic taste here, right? So I'm saying that the low is blue here, the high is red, and it has changed the particular representation of the color gradient. And I can put whatever I want here in this function, scale color gradient. If I say low equals white, because I'm in this mood here, then I get something that looks like that, which is totally unreadable, but never mind. You can also have multiple colors in the gradient, and I advise even less to do that. So it goes, for example, from a blue and then red and then white or something like that. So that's something I advise against, but there are ways to do this using this function scale color gradient here. Right, so you can have fun, make nice pictures, etc. when you prepare your Christmas postcards. Use scale color gradient. So what happens now if you use that and you revert not to a continuous variable, but to a discrete variable here? I remember that it used to work. So when we have when we did this plus g on point, it kind of made sense of the call. And so when we do that, if you have this scale color gradient and you want to pick the colors from a discrete variable, it says, no, I'm not going to be able to help you here. Like this is discrete values applied to continuous scale. It says, no, you cannot mix continuous values and discrete values. I will give you a different color for every species, but don't ask me to put them on a gradient here. These are discrete values. Okay, so that won't work. Now, one thing that if you do have to use a color map because you're forced to, or because you really want to impress your audience, like, you know, the defense, your graduation or something like this. If you have to, then please use that scale here, which is called viridis. So use that particular function, scale color viridis. And so this one here has a D in it, which means discrete. So viridis is a color map. So you can see that it has these purple here, and then bluish, and then yellowish. So it's taken 3 elements from this color map. And so why do I say if you have to use a gradient, use this one, is because it has been optimized for the human eye. So viridis is something that people work quite hard on it to kind of maximize discrimination power compared to other color gradients. So it's still a color gradient. It's still the fact that most people, everybody has to look up the legend to know the intensity of the colors, because this is not intuitive at all. There's no reason why it should be. But at least when you represent data with this particular contrasts, then it maximizes the distinction that we're able to make, and colorblind people are able to process it relatively normally. I don't know if there's a colorblind person in the audience, but if it's the case, then I'd be very curious how you see viridis, if it's really good for you to see the contrast. So it's been optimized basically to suit the human eye. So if you have to use a color map, my recommendation would be use this one. The package viridis actually comes with 4 color maps, which have kind of the same properties. And they differ just by the aesthetics, but they have the same discrimination power on the human eye. So if you use one, well, not use this one. So that's the function here, scale color viridis. And also I have to say that this is a color map that is now making its way through the scientific community. Many people are used to it as well. So using it is also now matching the expectations of your audience more and more. And what about if you want to not use the species here, but a continuous variable again, like the way that we thought we'd use a color map? If you do that, it fails because this little d here that you have stands for discrete. So what you want is to have a C for continuous. So scale color variety is continuous, and then it will be okay to do that. So here you can see the whole viridis color map in its full splendor. These are the this is the gradient of the viridis color map. And like I said, it's been made because almost everybody here has got maximal discrimination between these colors here, including people who are colorblind. At least one of the 2 types of colorblindness that is common. The other one, I think so as well, but I'm not entirely sure. So that's the color map that you will see quite often. And it's got 4 variants. And most of the time now in the publication, I see that people use that, which is kind of, it's nice. But like I said, do it only if you have to use a color map, which is most of the time not completely necessary. Right, so to wrap up this part, that's the usual ggplot call here. The geom point is to say that you want to scatter plot. You just say color equals and then a continuous variable. And just by adding plus scale color varieties underscore C for continuous, it does a lot of nice work for you with putting the legend here, coloring the points based on this variable that you specified. So looking good. So for a second. All right, so now finally, what we came here for, how do we add a regression line to a plot like this? Well, you keep adding things to the to this already busy lines. You say plus, I need to extend my screen, plus geom smooth. So this is the type of function that you need to add. One of the ways in which you can add regression lines in ggplot2. So geom smooth, you're going to smoothen the data. Method equals lm, and remember lm, we've seen it, and formula y regressed on x, remember we've seen that as well. So that tells ggplot2 what it needs to do in order to get that regression line. So when you do this, it takes a while. It's a bit longer than other methods. It does it, and wow, look at this. There's this nice funnel around it. This is looking so funky. So it's, of course, the now the match of the colors is pretty disastrous, but it does something which is kind of nice, which is it shows us the regression line. And it also shows us a confidence cone. I'm not sure it's a cone, confidence region around the line, where this is the confidence region where there is a 95% chance that the line falls into, at least not there is a 95% chance that the line is in this region, but the method uses like a protocol that guarantees that there's a 95% chance that the line is inside the confidence region here. And you can see that this confidence region is kind of wider at the extremes than in the middle. So we know a little bit better where's the center of the line, but the extremes, there's more wiggle way there and there. Like the uncertainty on the extreme is always bigger. So that's kind of nice. It gives us a regression line, not just a regression line, but also an idea of where this regression line is. It says, I think it's here, but could also be like that, pretty much horizontally we see, or even like looking a little bit upwards, it would fit inside this region there. So that's a nice way to represent the line. And if we don't want the this beautiful confidence cone, the way we do it is that we say SE is false. Okay, so just saying that SE is false, then it plots the line again, but this type, just the blue line here. And if you want another color because you don't like the blue, you think it doesn't match very much with your beautiful background, you can put a much more beautiful red or something like this. So within that geom smooth here, you can add some more aesthetic information to change the color of the line, its thickness, etc., or the presence of this confidence region. So that's the way you would do it using ggplot2. And again, it's using this LM method with the formula that's here that we've seen at the beginning of the class. So that's it. That's what I wanted to share with you today. Are there some burning questions before we wrap up? Yes? Sorry, what? When is the exam date? So officially, I've said in the syllabus that it was December 5 was the limit, because we are under relatively strict rules to put this before the actual exam period, because this is not an in-class exam. But I would like to put it a few days later, if you're okay with that. Sorry, what? 15th? On the corner, they say that the final exam is on the 15th of December.
It's like a 1 week window with the last day being December.
Yeah, I'll make an announcement. So what I was thinking is going to be around 8, 9 or something like this. But so these things I cannot really change too much the date, unfortunately, because it's whatever they say on this. It's registered at another date for me, and they're giving me 1 week after the time I gave them to give them the grades.
The last year Sunday,
What then?
like instead of 8, 9, you keep like 11 to Sunday.
You want to have it on a Sunday?
No, like the last day of submission.
So you want to be able to do it on the Sunday, right? So that you can work until Sunday late and Sunday. That's what you're saying.
I have exam like Friday. I have pre-exam in 2 days, bro. You're saying you want it to December and you want it until December 11th? Yeah, instead of 8 or 9.
Buy online.
Like,